before we define vector spaces, we need to talk about some examples of vector spaces. So the first example is going to be R3 or R2. R2 is defined as a list with elements A and B, where A and B are real numbers. And R2 is not a list, like I said it was. It's actually a set of lists. It's all lists where the elements are all possible real numbers. R3 is A, B, C. It's some list. So an element in R3 is some list where with 3 elements, where all of those elements are real numbers. Now, when learning about vector spaces, it's useful to generalize specific sets of vector spaces together. One of these generalizations is Fn. Fn is x sub 1, x sub 2, all the way to x sub n. So it's all lists of length n where x sub j for all j, 1, 2, all the way to n, are, and it's clearer to write this over here, are either real or complex. So F means real or complex, and the 4, 1, 2 to n means that all of these numbers belong to F. They are elements of F. And the list grows and shrinks with n. So an element in the vector space Fn is a list with n elements, where each element is either a real or complex scalar value. So, for example, R2 would be F2 for real numbers, and R3 would be F3 for real numbers. And if we had C5, that would be the set of lists where every element is complex and the lists have a length of 5. And it's important that they're lists and not sets, because in a list, 1, 2 is not equivalent to 2, 1. But in a set, 1, 2, where 1, 2 is a set of cardinality 2, is equivalent to 2, 1. Okay. Sometimes when we have a vector in a vector space, we write it as a shorthand variable. So if I had x plus y, where x equals 1, 2, and y equals, say, 3, 1, this is equivalent to 1, 2 plus 3, 1. And we define an addition on a 2 vector. So let's define addition on 2 vectors in Fn. So we'll call x so this first vector is called x, and x is in Fn. It is a vector in Fn. And we'll take some vector y. Okay. To add these 2 vectors, we take one scalar from an index and add it to the scalar from the opposite vector at the same index for all indices. So x1 is added to y1, x2 is added to y2, all the way to xn and yn. And we'll call this z. So x plus y equals z. So if we ever write 0 in the context of vector operations, we mean to say that 0 is an identity vector, or it is the additive identity on a vector space. So take some vector from a vector space, adding the 0 vector to some vector in our vector space just gives us the original vector. And for Fn, so for all vector spaces that are inside Fn, that's just going to be zeros for every value of n. So it's going to be a list where each element is 0 and the length is n. Because we're basically adding 0 to all of these values. We're just after we do that, we're just going to get those values, and it's going to be an identical vector. And let's see, what else should I cover? Okay, so, and then we're going to talk about scalar multiplication. You might want to multiply vectors together, but this this has no simple... We could conceive of multiplying two vectors together as taking the scalar from each index and multiplying them together and getting a resulting vector. But this is less useful than what we actually use for vector multiplication, which is beyond the scope of these notes. So we're just going to talk about scalar multiplication. Scalar multiplication takes, say for some s, which is a scalar, in F, which is the set of scalar values. We say that S times some vector x, where x is in Fn, and S is in F, our scalar set, is equal to each element of x times S individually. And this has some nice properties. Because we're multiplying all the terms by a factor, if we visualize a vector as an arrow, our factor of S is the amount we scale this arrow in space. So if S is multiplied by 2, the size will double. If it's multiplied by -1, it'll flip. And we cannot change its angle with any scalar value unless we're also flipping its direction. And this is just because we basically get a triangle from all of our components or all of our elements in this list. And if you multiply the opposite and adjacent sides of a triangle by the same factor, you're going to get the same angles. And that's why the angle of this vector doesn't change. And something I forgot to talk about before is that adding vectors has a nice intuition. If you add, say we have two vectors visualized in R2. So we have these two vectors in R2. If I add them, then we can imagine taking the beginning of one vector and positioning it at the tip of the other vector. And then the tip of our initial vector is the resulting vector from that addition. Okay. And then the reason that's all I will be doing in these notes. Or now that we've shown an example of a vector space and the operations you can do on particular vector spaces, we're going to define very broadly what a vector space is. So a vector space is a set and operations that go along with that set. So we'll say the set will be, the vector space we'll call V, and we need to guarantee that we've defined an addition operation onto V and also a multiplication operation onto V, and that's scalar multiplication. We don't need to define multiplication on two elements in our set. So, along with these two operations and our set, we need to in order for this vector space to be a vector space, it must have the following properties, definitionally. It should have commutativity. So if you take your set and pull out any two vectors from that set, say V and W. Okay, if you add them together in one order, you should be able to add them together in the opposite order and get the same value or the same result. So it's vectors in a vector space when added together should be agnostic to order. And that's commutativity. And then there's associativity, which says that if you have three vectors in your vector space, say V, W, and Z, it doesn't matter how you group these parentheses here. The resulting vector should be identical. That's associativity. And then a vector space should also have an additive identity. And what that means is if you have some vector V in our vector space, there is some vector called our additive identity, and it looks like 0, such that if you add the additive identity to every vector, you will get that vector, that initial vector. And then there's also the additive inverse, which says that for every vector V in our vector space, there is a vector, we'll just say W, such that when you add it to that initial vector, or that arbitrary vector in our vector space, you get the additive identity from here. And then there's also the multiplicative identity, which just says that if you multiply a vector in the vector space by 1, then you will just get that initial vector. And then there's the distributive properties. So take some scalars, A and B, in our scalar set. And we'll take some vectors V and W in the vector space. And the distributive property guarantees that A times our two vectors added together is equal to A times one vector plus A times the other vector. And the other distributive property is that two scalars A plus B times some vector V is equal to AV plus BV. And if you meet all these criteria, and you've defined your operations, and you defined a scalar field for the vector space to act on, then you can call that set in operations a vector space. Use our definition of a vector space to prove some other useful properties about vector spaces. So every vector space has a unique additive identity. And to prove this, let's suppose that there's two additive identities. One's marked 0 and the other is shown as 0 not, with this little guy up here. We know that 0 equals 0, and we know 0 not equals 0 not. And we also know that because they're both additive identities, we can add them to either side of the equation without changing the value of the side that it's on. So we can add this additive identity with the prime to the initial additive identity, and we will get the initial additive identity. And also we can add our first additive identity to the additive identity prime and get the value of the additive identity prime. And you'll notice that these two sides of our separate equations are exactly the same, which means that these two things are exactly the same, which means that both of our hypothetical additive identities are equal to each other, which means there's only one. All right. The other proposition is that every element in a vector space has a unique additive inverse. So we have some vector v, and then we add to it some additive inverse, and we get our additive identity. To show that there's only one additive inverse, oh, this is easy. Let's suppose there's two additive inverses. Inverse and inverse prime, like this. So we know v plus w equals 0, and we know that z plus w prime equals 0. We can just set v... these two, the right side of both equations are equal, so we can set the left sides equal to each other. And then we get v plus w equals v plus w prime. And then we can just subtract v from both sides, and we get w equals w prime. And so if our two hypothetical additive inverses are equal to each other, then there's only one of them. Let's see. Okay, the other proposition is that... Okay, take some scalar 0 in f, and we're going to multiply that by some vector v. The proposition is that this equals our additive identity. And to prove this, I'm going to need to... Okay. We have to use the distributive property for this one because it connects scalar multiplication to vector addition. So let's just say our scalar 0 is equal to 0 plus 0 multiplied by our vector. And actually, I'm presupposing that this is equal. So I'm going to start... Okay, I'm going to start with nothing. Okay, let's just take some vector 0, and we'll say it's equal to 0 times itself, which is true. I'm going to... We know that scalar 0 equals 0 plus 0. And so we can rewrite that as such, and then we get this new... We get the same equation written a different way, and then we can just distribute. So then we get v0, 0v plus 0v equals v equals 0v. I forgot to bring down the 0. And okay, we're going to add the additive identity to this side on the right because we know that it doesn't change the value of the side of the equation. And then we can just subtract 0 times v from both sides. And we get 0v equals 0 times v equals our additive identity. All right. So we had to leverage the distribution rule to show that. And I'm satisfied with that. Okay, the other proposition that we're going to prove is... Okay. And then lastly, we're going to show that a scalar -1 times some vector is equal to its inverse. Okay, so let's start with that -1, and let's set it equal to itself. The -1 scalar times a vector. We're going to also add 0 times v. which we showed before to be our additive identity. Just to one side, though. And we know that a scalar 0 equals 0 plus 0. So we're going to rewrite that. And then rewrite our whole equation. Okay. Actually, it's more useful to say that it equals 1 minus 1. Okay, and then we get this long equation. Negative 1 times v equals negative 1 times v plus 1 times v plus negative 1 times v. Okay, now I'm going to subtract negative 1 times v from both sides. And then we get our identity over here. And then we get negative 1 times v plus v is equal to our identity, and which means this is an inverse, because when we add it to our vector, it becomes our additive identity. So that is definitionally what an inverse is, and it's also the only inverse because we proved that before. And so negative 1 times v is equal to our inverse. And that's the last proposition.